If I ask you to predict if something is present or not present, just based on one piece of information, how would you do it?
Hmm.
This is a good situation to apply logistic regression. Back in episode 503, I covered a machine learning approach to logistic regression. Today, I'm going to show you a Bayesian approach. So what's the difference between linear regression and logistic regression? And what's the difference between a machine learning approach to logistic regression and a Bayesian approach? Well, let's find out. Welcome to Dago.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. In the interest of time, I've prepared some code and an interactive Pluto notebook in advance. You can find a copy of my code and a copy of this Pluto notebook in my GitHub repository. There's a link to my files in the description below. If you want to follow along, you can save a copy of these files in a tutorial folder on your computer. After you save the files, in VS Code, launch the Julia REPL by using Alt-J, then Alt-O. Change the present working directory to your tutorial directory. Enter the package manager by using the closing square bracket. Activate the tutorial directory. Add the following packages: CSV, statplots, and Turing. Exit the package manager by hitting backspace. In the editor, execute the code to load the packages. Okay, now that we have our packages loaded, let's download some data. In 2006, a trio of scientists in Japan published a research paper that included a survey of the habitats of an endangered burrowing wolf spider, Lycosa ishikariana, that lives along the coast of southwestern Japan. The habitats of the species are threatened due to human activity along the beaches where the wolf spiders have historically called their home. To aid conservation efforts, the researchers set out to discover the environmental factors that affect the occurrence of the species. In their research, they determined that the median grain size of the sand on the beach is one of the most important factors to use when trying to predict the presence of the wolf spider at any given location. As a motivating example, we're going to use their dataset as a way to learn about Bayesian logistic regression. I'm executing the code to download the data off the internet and into a CSV.file data type. If you're typing in this code manually, you can find a copy of this URL in the description of this video. This file contains two columns. Column 1 contains the feature information, and column 2 contains the class information. The code that I'm executing now will convert the CSV.file data type into a Julia matrix. Click on the Julia logo icon along the left-hand side of VS Code and look for the data_matrix variable. Click on the table icon on the right side of that line. Column 1 contains the median grain size of sand found on the beach measured in millimeters. If you click on the column 1 header a couple of times, you can see that the range of the median grain size is between 0.2 millimeters to 1.1 millimeters. Column 2 contains either a 1 or a 0, indicating whether or not a wolf spider was present during that observation. 1 means present, and 0 means absent. This dataset contains 28 observations, so there's not a lot of data. In any event, Now that we have our data, let's visualize it. The values along the x-axis show the median grain size of the sand in millimeters. And the values along the y-axis are the probabilities of a wolf spider being present, which in this case is either a 1 or a 0, with no values in between. There's quite a bit of overlap between the 1s and the 0s. The challenge here is to come up with a model that you can use to predict whether or not a wolf spider will be present just based on the median grain size of the sand on the beach. Because of the nature of this data, you can't use linear regression, because you won't be able to find a good fit for a straight line through this data. Instead, what you really need is some curve that starts near the point 0, 0 in the lower left corner of this plot and ends in the upper right corner of this plot. This curve needs to travel from left to right along the x-axis when y equals 0 until x equals roughly 0.3 or 0.4. And then the curve needs to bend up quickly to where y equals 1, and then continue traveling left to right along the horizontal line where y equals 1. This sounds like a good job for a sigmoid curve. So, what's a sigmoid curve? Before looking at a sigmoid curve, let's start with a definition of a straight line, which is y equals mx plus b, where m is the slope of the line and b is the y-intercept of the line. Next, let's take a look at the definition of the sigmoid function, which is 1 divided by the sum of 1 plus e to the power of negative x. The sigmoid function is a special case of the logistic function, which defines a collection of S-shaped curves, including the sigmoid curve. The problem with the sigmoid function, which defines the sigmoid curve, is that the function doesn't contain any parameters. As a result, you can't change the shape of the sigmoid curve by using this equation the way that it's currently written. But a clever trick is that you can replace the variable x in the equation with a function that defines a straight line. By doing that, you can modify the slope and the y-intercept parameters to alter the shape of the sigmoid curve. Let's take a look at an interactive model that will demonstrate what I mean. In this interactive model, the sliders for the slope and the intercept control the shape for both plots. Before moving any sliders, notice that the range of the x values in both plots is between -10 and +10. Well, the range of the y values in the top plot goes from -10 to +10, while the range of the y values in the bottom plot only goes from 0 to 1. By plugging in the equation for a straight line into the sigmoid function, what the sigmoid function is really doing is taking the line from the top plot and squeezing the y values down so that the y values fit in between 0 and 1. Also notice that in the top plot, the line crosses the y-axis at 0, which is the y-intercept. But in the bottom plot, the curve crosses the y-axis when y equals 0.5, since the range of the y values is now only between 0 and 1. Notice what happens when you increase the slope. Increasing the slope makes the line in the top plot more steep, going from left to right. A similar change happens to the sigmoid curve in the bottom plot. If you change the slope to 0, then both plots are the same horizontal line. When you change the slope to a negative number, the line slopes down from left to right. At the same time, the sigmoid curve on the bottom flips and starts along 1 and then moves to 0, going from left to right. So by using the equation for a line inside of the sigmoid function, you can control the shape of the sigmoid curve in a manner that's similar to the way you can control the shape of a straight line. It's the same line, but the y values have just been squished in between 0 and 1. Now try changing the values for the intercept. By increasing the intercept from 0 to 5, the line crosses the y-axis at 5. But in effect, increasing the intercept shifts the line from side to side in the plot. The same thing happens to the sigmoid curve. By increasing the intercept, you're effectively shifting the sigmoid curve from side to side. By tuning the values for both the slope and the intercept, you can alter the shape of the sigmoid curve to fit your data. We're going to use this concept when defining our Bayesian logistic regression model. The model that we're going to use for a Bayesian logistic regression approach is very similar to the model that we used for a Bayesian linear regression approach. Okay, let's talk about this model. In this model, we're saying that the presence of a wolf spider is a function of the median grain size of the sand at the beach. Like in our Bayesian linear regression model, this Bayesian logistic regression model holds prior beliefs for both the intercept and the slope parameters. By using these definitions, what we're saying is that we're really not sure what those values are, but we believe that the intercept should be some negative number and the slope should be some positive number. A positive slope would generate a sigmoid curve that starts near 0 along the left-hand side and then move up to 1 as the curve moves from left to right. A negative intercept would shift the curve from left to right. Shifting the curve will allow us to focus on the positive values along the x-axis, which measures the median grain size, since we know that the median grain size will always be a positive number. Here's what the PDFs look like for uniform distributions with ranges from -5 to 0 and from 0 to 10. These represent our prior beliefs about the probability distribution of the values of these parameters. For the likelihood, we start with a deterministic function for a line, which we use in the Bayesian linear regression model. But in this Bayesian logistic regression model, we have a second deterministic function for the equation of a sigmoid curve. We're plugging in the equation for a straight line into this equation, like we discussed when viewing the Pluto notebook. P stands for the success rate, used in a Bernoulli distribution function. The Bernoulli distribution is a discrete probability distribution that is a special case of the binomial distribution. The Bernoulli distribution is used for a single event, where the outcome is either 1 or 0, like true-false or heads-tails. The Bernoulli distribution takes a single parameter, p, which is a value between 0 and 1 inclusive. A value of 1 means 100% success, and a value of 0 means 100% failure. The failure rate is 1 minus the success rate, so the sum always adds up to 1. In our case, we're using the Bernoulli distribution since the presence of a wolf spider will either be present or absent. There's nothing in between. Because the Bernoulli distribution is only for a single event, we need to use a for loop to ensure that each row of our likelihood is distributed as a Bernoulli distribution. So that's our Bayesian logistic regression model. The biggest difference between the Bayesian linear regression model and the Bayesian logistic regression model is how we define the likelihood. Now, the rest of the workflow is pretty similar. The inference step is essentially the same as we've seen before. In the summary statistics table, the mean value of the intercept is around -2, and the slope is around 6. That's consistent with our prior beliefs that the intercept was some negative number between 0 and -5, and that the slope was some positive number between 0 and 10. As long as we're here, I want to point out another set of numbers to be aware of when looking at the summary statistics table. The R-hat column is an important diagnostic metric to check. This metric measures whether or not your chain has converged on a solution. What you're looking for is a value of around 1. If that number is too high or too low, that's a red flag that something may be off in your model. But these R-hat values look fine for this example. We'll go through the numbers in these other columns in future tutorials. For now, let's visualize our chain. The plots on the right-hand side are the approximations of the posterior probability distributions for our parameters. These represent our updated beliefs after seeing the data. As a reminder, here are the prior beliefs. It looks like the posterior distributions are some type of Gaussian distributions, but there's a fairly wide range of values for both the intercept and the slope. Let's take a look at how these parameters translate to our plot with the observations. For this, we're going to use a for loop to loop over each row in our chain and draw 1,000 sigmoid curves based on the parameters sampled in each row. Don't forget, you need to call the name of the plot to display the updated plot. So, this is an interesting plot. This plot shows 1,000 sigmoid curves, based on the parameters in our chain. There are a lot of different curves, but the darker band indicates the area of highest concentration. This plot captures our uncertainty. Even when the median grain size is 0, our model is showing that there's still some probability that a wolf spider may be present, which is physically impossible. But the darker bands suggest that detecting a wolf spider when the median grain size is 0 is highly unlikely, and the probability of detecting a wolf spider increases as the median grain sizes get larger. Pretty cool, right? Now, you can use this Bayesian logistic regression model to make predictions, just like we did with our Bayesian linear regression model. For our predictions, let's test median grain sizes of 0.25 millimeters, 0.5 millimeters, 0.75 millimeters, and 1.0 millimeters to see what type of predictions our model generates for these data points. Because our model is using a Bernoulli distribution, which only works for a single event, we need to use a vector of missing values in order for the predict function to work properly here. In the summary statistics table, you can see the mean values for the predictions. For the 0.25 mm test, our model predicts that the mean success rate is around 40%, so the chances are low, but not zero. For the 0.5 mm test, our model predicts that the mean success rate is around 70%, so the chances are pretty good. For both the 0.75 mm test and the 1.0 mm test, our model predicts that the mean success rate is around 90% or higher, so the chances are extremely good. But before you get too excited, notice that the standard deviations are pretty high for all of the predictions, which indicates that these predictions have fairly low confidence. If you look in the quantiles table, you'll see a matrix of potential predictions. Let's visualize these predictions to get a better idea of what's going on. There are 4 sets of diagnostic plots here, one for each prediction. Rather than showing a PDF, the plots along the right-hand side are showing histograms of the frequencies of either zeros or ones. The sum of the frequencies adds up to 1000 for the 1000 samples in our chain. So in the top plot, the histogram is showing that it predicted zeros more times than ones, suggesting a lower success rate. In contrast, in the bottom plots, the histogram is showing that it predicted ones almost all of the times, suggesting a very high success rate. If you click on the Julia logo icon and click on the table icon for the predictions variable, you can see the details behind these predictions. So the predict function went through each row of the chain, and based on the parameter values in that row of the chain, it made a prediction of either 0 or 1 for each of the 4 test values. It did that for all 1000 rows. The histograms are just adding up the zeros and ones in each column. Fascinating, right? The workflow for Bayesian logistic regression is very similar to the workflow for Bayesian linear regression. The biggest difference is that for Bayesian logistic regression, we're looking for the parameters that define a collection of sigmoid curves, rather than a collection of straight lines. Like with Bayesian linear regression, Bayesian logistic regression returns probability distributions, which reflect our uncertainty based on the data that we've seen so far. This allows us to make predictions using the language of probability distributions, as opposed to using concrete numbers, which will almost always be wrong. As for the difference between a Bayesian approach to logistic regression versus a machine learning approach to logistic regression, the machine learning approach returns a result that is similar in concept to creating a linear regression model using the ordinary least squares method. The machine learning approach converges on one best fit sigmoid curve, which is similar in concept to the linear regression line. By using this best fit curve, you'll be able to make confident predictions like you can using an OLS linear regression line. But since the machine learning model doesn't provide you with a probability distribution around a range of potential solutions, your predictions using the machine learning approach will often be wrong, without providing you with any insights as to why your predictions are wrong. This will be a recurring theme throughout this Bayesian series. A Bayesian approach is a more nuanced way of looking at a world full of uncertainty. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, then please consider liking, commenting, sharing, and subscribing. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free, early access to all of my new videos. Thanks for watching, and good luck on your Julia journey!